If the rogue planets of deep space are the galaxy's silent wanderers, their opposites burn in furious captivity. These are the extreme worlds, planets pressed so close to their stars that rock melts and metals flow like rain. Others swell to impossible size, ballooning until they outgrow the very stars that birthed them. Across the Milky Way, these infernos and giants reveal the upper and lower edges of planetary existence. How hot, how massive, and how strange a planet can become before it crosses into something else entirely. Where heat becomes a landscape, our sun blisters Mercury to nearly 800 degrees Fahrenheit, 430 degrees Celsius, hot enough to melt lead. Yet even that is tame beside the ultra-hot Jupiters found by modern telescopes, giant gas worlds dragged almost against the faces of their stars. One of the most studied is WASP 76b, discovered in 2013. Orbiting a yellow-white star 640 light-years away, it completes a full revolution in less than 2 Earth days. Its orbital distance is so small that the star's outer atmosphere brushes against the planets. Astronomers estimate daytime temperatures around 4,400 degrees Fahrenheit, 2,400 degrees Celsius, hot enough to vaporize metals. WASP 76b's dayside never knows darkness. The heat splits molecules apart. Even iron turns to gas. Blown on supersonic winds across the planet's terminator, the thin border between day and night, the vapor cools and condenses, falling as molten iron rain on the night side. It's a world of endless thunderstorms of metal, where the concept of weather borders on alchemy. Through spectral fingerprints in the planet's light, the Very Large Telescope in Chile confirmed iron's telltale signature, proving that this alien rain is not myth, but measurable fact. No poet could have imagined a sky more unforgiving. Far worse waits deeper in space. Meet Kelt 9b, discovered in 2016, a gas giant almost twice Jupiter's size, orbiting a blazing blue star only 5 million kilometers away. Kelt 9b endures dayside temperatures of 7,800 degrees Fahrenheit, 4,300 degrees Celsius, hotter than the surfaces of many red dwarf stars. Here, molecules cannot survive. The atmosphere dissolves into atomic plasma. Hydrogen streams away into space at a rate of hundreds of thousands of tons per second, forming a comet-like trail torn toward its star. Within a few 100 million years, the planet will be a stripped core, or consumed entirely when its sun expands and devours it. On Kelt 9b, there would be no solid ground, no horizon, only a storming ocean of vapor churning above a gravity well deeper than imagination. To watch it from orbit would be to see a furnace glowing against black space, bright enough to cast shadows halfway across its system. Such worlds are found mostly because they announce themselves. The transit method, which measures minute drops in a star's brightness as a planet crosses its face, favors close-orbiting giants. Their bulk blocks more light, and their rapid orbits offer frequent repeats for confirmation. Ironically, that bias explains why many of the first exoplanets discovered were monsters hugging their suns. Not because they dominate the universe, only because they shout the loudest across the void. But every scorching orbit we map helps redraw the boundaries of possibility. If Kelt 9b teaches us how bright a planet can burn, other discoveries reveal how large a planet can swell before physics rebels. By definition, a star becomes a star only when its mass exceeds 8% of the Sun's, allowing hydrogen fusion in its core. Below that, objects remain brown dwarfs, failed stars that glow dimly from residual heat. Still smaller lie the giant planets, some verging on the same scale. In this grey frontier, definitions blur. One candidate sits near that threshold, GQ Lupi b, a world, or perhaps a sub-brown dwarf, 3 times Jupiter's radius. Observed directly by imaging in 2005, it orbits a young star in the constellation Lupus. Its youth and heat make it radiant enough to detect without a transit. Yet scientists disagree whether it's truly a planet or a starlet that never quite ignited. Such ambiguity underscores how fluid nature's categories can be. Another record holder, WD 1856b circles not a bright star, but the ashen remnant of one, a cooling white dwarf about the size of Earth. Astonishingly, this giant Jupiter-sized planet whirls around its tiny host every 34 hours. That it survived the violent death throes of its parent star is miraculous. When the original sun swelled into a red giant, it should have engulfed everything within millions of kilometers. Somehow, WD 1856b avoided destruction, perhaps flung outward and later recaptured, or pulled inward by orbital ballet. In its dim sky, the white dwarf would shine like a pearl of unbearable brightness, small enough to eclipse behind a coin held at arm's length. If size were measured not by radius but by spectacle, the crown would go to J1407b, a planet roughly 400 light-years away, temporarily dimming its star in 2007. The pattern of light suggested an enormous ring system, 200 times larger than Saturn's, spanning nearly the orbit of Venus. For weeks, the host star's glow flickered in complex rhythms as countless rings crossed our line of sight. To observers on the planet's moons, the rings would fill half the heavens, bands of silver stretching unbroken from horizon to horizon. Astronomers believe these rings are temporary, a relic of adolescence. New moons will eventually sweep the material into narrower belts, just as Saturn's moons sculpted its rings into harmony. But for now, J1407b remains the greatest jeweled world ever glimpsed, a planet so ornamental it eclipses its own star. Extreme though they are, these Infernos and Leviathans are more than curiosities. Each provides a laboratory no Earth-bound facility could replicate. Hot Jupiters like WASP 76b test our models of atmospheric circulation and chemistry under impossible heat. Planets around white dwarfs unveil the final chapters of solar systems, how worlds respond when their suns die. And swollen ring worlds remind us that planetary systems are not static sculptures, but living things evolving before our eyes. More profoundly, these extremes show us where the boundaries of creation lie. What happens when gas pressure, heat, and gravity wrestle beyond their limits? At what point does a planet cease to be one? In seeking answers, we learn not just about distant worlds, but about the forces that once shaped ours. Our own Earth orbits comfortably within a narrow lane, neither seared nor frozen, neither ballooned nor stripped. Move us slightly closer to the sun, and our oceans would boil, slightly farther, and they would freeze beneath global glaciers. The Infernos and giants remind us how delicate this equilibrium truly is. The same laws of gravity and thermodynamics that create firestorms on Kelt and 9b also hold our climate steady. The difference lies in distance, scale, and chance, proof that life blooms in slender margins between extremes. In the fullness of cosmic time, worlds like WASP 76b and Kelt 9b are fleeting. Their stars will consume them or reduce them to cinders drifting in tidal rings. Even giants like GQ Loopy b will eventually cool, fading into invisible embers against the background of the galaxy. But though they perish, their discovery changes us. Each new name, each faint dip in stellar light, adds one more brushstroke to the portrait of existence. In the end, perhaps that is the real legacy of exoplanet science, to transform the sky from a handful of points into a living chronicle of endless diversity. One day, when our instruments have sharpened beyond sight's limits, we will no longer speak of planets around stars, but of the galaxy itself as a single living structure of light and orbit, an ecosystem of fire, ice, and possibility. From the scorched world where iron reigns to the gas giants that dwarf their suns, the universe displays a ruthless imagination. It crafts beauty from extremes, forging harmony through destruction and contrast. We began this journey amid the swiftest orbits, crossed the skies of many suns, wandered the starless dark, and now arrive at frontiers of flame and vastness. Together they form a panorama of what it means to be a world, proof that planets, like stories, come in every shape the cosmos will allow. As our telescopes reach farther and our minds follow, we realize that Earth's gentle balance is not the standard, but the miracle. Against the furnace, the void, and the storm, our small world floats in a calm between extremes, a brief candle glowing in a universe of fires large and small.